intro to integrals, okay, which is the opposite of derivatives, we're going to do a little reminder of what a derivative is, okay? But we're going to do it graphically. And so we just need quadrant 1. And we're going to draw 3 graphs, so don't draw it too big. Okay? And we're going to label this time. So we'll call this S for seconds. And we'll call this side height. And we'll use feet. Okay, just a little picture. That's it. This is typically called a position graph, and we're going to call it P of t, because t is the input. When I do the derivative, okay, time isn't changing for seconds. Okay, if I look at estimating the slope, we usually get change in y, change in x, which is a quotient. Okay, so we usually get change in y over change in x, but we're going to do it with the units in this graph. So that would be feet per second, right? Look at the units. It's just the y units over the x units. That's feet per second. Can anyone tell me the actual quantity that describes feet per second? Starts with a V. Velocity. Velocity, speed. Okay, so this is the velocity graph. Position, velocity. Okay. Now, it is. It's very similar to physics. So it'll be good because then you get to do it a slightly different way. No? Not good? Not good? You will be able to do it now.
It's so hard to understand.
No.
The whole class thinks I'm dropping because I don't understand anything.
Now you will understand it, okay? Because we're going to go through.
Coming to me the other day, they're like, didn't you drop this class? Like, we thought you weren't in it.
All right, so hold on. So we're going to write P prime. Okay, the derivative of position equals velocity. Based on the units alone, that should make sense. Slope of this graph gives me the units of velocity, and so you can call it the first derivative or velocity. Okay, so we're going to do it one more time, except I'm going to put feet per second on the y-axis because that's what I'm plotting. I actually plot the slope number. Okay. If I do this one more time, the second derivative of position equals the first derivative of velocity equals, okay, so I'm just going to pretend to do slope of this graph. We'll draw a little picture. It doesn't really matter. Okay, we're not drawing anything to scale. How would you do slope of this? Well, we've got seconds here, right? Seconds is the change in x, and the change in y is already feet per second. So what do you get for units when you do slope of that graph? Acceleration. Feet per second per second. You divide by seconds twice. Acceleration. Notice that I'm using V and A, right? Velocity, acceleration. Acceleration implies that you're doing the second derivative of the starting graph.
Oh my gosh, wait, that makes so much sense.
she took this before.
I know. Okay. I know.
She does so well in physics because she's in BC Calc, and she's like, you just take the derivative of it. I'm like, why?
Okay, so, all right, so derivatives.
Why didn't you tell us this about this?
They should really let you know that you should take.
Okay, basically derivatives are a quotient. You divide the units. Derivatives are quotients. Next, the second column is going to be integrals. All right. Integrals are products, right? Derivatives are quotients. Integrals are products. And so it's going to be change in y times change in x. That is the operation of how you're going to find integral quantities, right? We have derivative quantities, slopes, rates of change. We have integral quantities, which is the product of change in y and change in x. And so we're going to review some of your area formulas, because when you multiply two things together, you get length times width, or area. Okay, so we're going to draw length, width, okay, area equals. I'm going to draw the shapes. You write in the area formulas. Okay, and the last one. It's my favorite shape. Okay, so you get a length times width, right? Rectangle, okay? Got it. 1/2 base times height. All right, not so bad. Pi r squared. And a trapezoid. Okay, so I'm going to draw something. See if you can figure out what the formula is. If you cut that little triangle piece out and you fold it over, makes a rectangle.
It's just kind of different.
Which means it's very similar to my first formula, but you kind of have to put it in terms of the measurements that you have.
The difference of V2
So,
and V1.
I do have to multiply by height because I've got that measurement. But like, what is the length of this new formed rectangle? It's called a trapezoid. I turned it into a rectangle. Yes, it is. So what if you just average B1 and B2? Right? Average B1 and B2. It gives you the height of that rectangle. So that's B1 plus B2 over 2. Now there's a reason I'm drawing the trapezoid like this, because that's how it's going to look when we draw it in our notes. Okay? And I prefer to put my 2 in front because I don't feel like averaging. I prefer to write the formula like this. It's easier to type. It's easier to calculate. I'll just take that divide by 2 and put it in front. This is the easier formula, and this one's called a trapezoid. I do expect you to have these formulas memorized. Like, you need to know these area formulas. I'm not going to write them up on quizzes or tests. You're going to have to know them. Okay? We're going to do a lot of practice with the area formulas, so you should know them. Okay. We're going to do a little activity with the intro to integrals. Okay. Most of it is self-led. Okay. We're going to stop and talk about parts of it along the way. Make sure you have a calculator handy. Okay. You're going to learn some really cool buttons in your calculator today, so make sure it's handy. Okay. There you go. Try again. It's totally, no, you don't need to know physics, but if you do, you'll be like, oh my God, that's what they were saying. So no, you don't have to know any physics to do this. No. Some of it you'll see some connections, but it's not necessary. All right, let's go ahead and start reading. Okay, it's mostly self-directed, and I will stop you at different parts and make sure you have some things written down. Okay, so you're doing questions 1 and 2. Read the description and do questions 1 and 2. Try to include units with your answers because our graphs have units. Right, we're looking at a velocity graph, time versus velocity. So make sure you have units in your answer. You're doing questions 1 and 2. No, shade it, because we're going to shade something else also. Shade the rectangle.
The area under the slope from 30.
Too much. Don't shade here. Stop at the top. Okay. Nice. Okay, so what does your velocity seem to be between 30 and 50? Okay, so here's 30 and here's 50. So my velocity equals 60 feet per second. How far do you travel? Now it's 60 the whole time, constant rate. So 60 feet per second times 20 seconds. Look at my units. The seconds cancel out, and you're left with 1,200 feet. They asked me how far do I travel. Means your answer should be feet. I traveled 1,200 feet. And then it says, explain why the answer to problem 1 can be represented by the rectangular region. Okay, so I'm going to shade said rectangular region. Seems to make a rectangle. Okay, there you go. Okay, how does that work? Well, I have length times width. The area is 20 seconds, right? You've got to include your units. 20 seconds and 60 feet per second. Still cancels. 1,200 feet. Notice that a product, change in X, change in Y, is the integral quantity. Okay. Number 3. The distance you travel between 0 and 20 can also be represented by the area bounded by the curved graph. Count the number of squares in this region and estimate the area of parts of squares to the nearest point 1. Okay, so how would you count that square? Looks like maybe 0.6. It looks a little more than half, but not quite 3/4. Okay, so estimate the area between 0 and 20. So I'm going to shade it, and then you're going to estimate it. 0 and 20. Here's the section it's asking you to find the area of. Okay, that's what it wants you to find the area of. Estimate to 0.1. Okay, so you are doing questions 3 and 4. Questions 3 and 4. I try to count as many whole squares as possible and then start combining the partial squares. Okay, so you should have gotten, let's see, about 24 is one section. Point nine. Right, I'm just checking boxes off as I add them up. Okay. Point. Point 2. Okay. 0.6. 0.2. That one maybe looks like 0.5. This one, I'm trying to compare it to half of it and then estimate my decimal from there. 0.2. Okay, so we get 25 plus 0.9 plus 0.9. 0.2 plus 0.6 plus 0.2 plus 0.5 plus 0.2. So I get approximately 28.5. Now, I understand everybody counts and estimates differently, but you should not be off by more than like a half of a square. So you should have an answer anywhere between like 28 and 29. Maybe 0.6 off, but you should be pretty close within those two integers here. Okay? Especially because 24 of them were solid squares. You were only estimating a few of the squares here. It's just these ones on the edge that you're estimating. Okay? It means you should have been pretty close. Okay, so we get 28.5 squares. Okay, so let's see what question 4 asks. Question 4 says, how many feet does each small square represent? Okay, so what does one full square represent? It means I have to check my units. Okay, so I look at my graph. One square is 5 seconds, and this is counting by tens. Now look at that. That's a velocity graph, which means this is feet per seconds on this axis. When you multiply them, okay, you get just feet. Okay, so it's 10 feet per second and 5 seconds. So 1 square equals 50 feet. You have to include your units. Okay? So therefore, how far did you go from 0 to 20? Well, 28.6 squares times 50 feet per square. 1425. That's how far I traveled. Within 50 feet on either side, right? Depending upon what you estimated, 1375. Oh, no, I said half a square. Between, right, your answer, because we all estimated, should be between 1400 and 1450. Pretty close between there. If I ask you to estimate on a quiz, you have to show your work so I can follow your work. You all count up squares differently. Okay. 5 we're going to do together. Problems 3 and 4 involve finding the product of the x value and the y value. Okay. Such a product is called the definite integral. So we're going to write some notes over here. The definite integral we're going to put some notation here. it kind of looks like a really tall S. Kind of like for some. Okay. Now we're going to write V of t times dt. And we're going to say T1, T2. I'm going to tell you what all these things mean. Okay. This is the notation for the definite integral. T1 is the start time. T2 is the stop time. Where did you start adding up the squares? Where did you stop adding up the squares? V of t, that's actually the y value, right? Look at the units on the graph. V of t is the y, dt is the x coordinate. Because definite integrals are a product of x and y. And the s part, this part, that is actually the integral symbol, okay? I like to say sum because you're adding up the areas from the start to the stop. This is an integral. Okay, so we're going to write two integral statements. Question number 2. The integral from 30 to 50, right? Isn't that the first one we did? From 30 to 50, V of t dt equals 1,200 feet. That was the first area we added up. That's the notation that says I added up the area. I started at 30 and I stopped at 50 velocity. That was the name of the graph I was looking at to add the area. Okay, question number 4. From 0 to 20, from 0 to 20, I was adding up the area, summing, because the integral looks like an S, summing up the area under that graph. V of t names the graph that you're looking at. And we ended up with 1425. Now, you could probably put approximates here because we were estimating this area. Yes, Erin.
For number 4, 14.5, is that the area of just the light?
Of just this, no, that's the whole thing because there was 28.2 squares total, right? You had the rectangle area that was 24, and then you added up all those partial areas at the top. Yeah? Okay. What I'd like you to do, okay, keep in mind, okay, that is just explaining the definite integral notation. I want you to evaluate this integral. Question number 6. Estimate the definite integral of this picture. This picture has a name. They're just calling it y, right? They didn't actually give it a label. It's just y. Okay, so let's maybe pick a label for it. Let's call it f of x. Okay, estimate this definite integral. 0 to 12 f of x dx. Now the questions are going to lead you through how to do this. That is the definite integral I would like you to find based on this picture. Okay? You need a number, and you need units. Tell you to start adding at 0 and stop adding at 12. I'm going to shade. Oh. That's the area that the definite integral represents. You estimate how you want. I would probably section off all the whole squares and then count up the partial squares. It's pretty symmetric, so use that to your advantage. So I got 36 full squares, and now I'm just going to try to estimate the other ones. I do notice it's symmetric, so I'm going to use that to my advantage. Okay. Okay. Point 6. Point 3. Point 6. Okay. 1.9, 2.4, 2.9, 3.5, 3.8, 4.4, so 8.8. Okay, so I get about 44.8 squares. Right, within a half to 0.75 squares, right? You should probably be between 44 and 45 and a half, right? You had a lot more partial squares to estimate here. Now, I just assumed this was symmetric, and I only counted up half of it, and I assumed the other side was exactly the same, right? Maybe I'm right, maybe I'm wrong, but that's what I assumed. You can see by me putting the times 2, and I'm only check marking half the squares, I just assumed the other half was the same. Okay, so 44.8 squares. What's each square worth? Okay, keep going. You're going to have to look at your units to figure this out. X is in inches. And graph shows cross-sectional area. Y is square inches. Okay, so I put units on my graph. Inches and inches squared. What are the units? So change in Y, change in X, inches squared times inches cubed. All right, definite integral means multiply the units. I get inches cubed. Inches cubed. What quantity has cubic inches? Say it. Volume. So what are the units? Okay. Therefore, what quantity? It represents volume. Whether or not it makes sense of how you get volume, you should understand that cubic inches is a volume measurement. That means that whatever you found, that number, that's a volume number based on the units alone. Now, I'm not quite finished because I don't have my number yet because I only have 44.8 squares and I need to figure out what each square is worth. So here I'm counting by 1 inch. Here I'm counting by 5 inches squared. Okay, so 1 square is 5 inches cubed per square. Okay, 44.8 times 5. 224. 224 inches cubed. The volume of the football is 224 inches cubed. Okay, so I can start at 0, stop at 5. The name of the function is f of x dx, and the area was 5 times 3. Okay, you're going to press math. Scroll down. You see this f int.
Yes.
Press enter.
Wow.
Fancy. Okay, 0. You're literally copying what you typed here. Okay, except you can either type f of x, which we don't have, or you can just type 3, because that's what it was. That was what it's actually equal to. And then dx. Press enter. Oh, it'll give you it. Now this is the exact answer. Okay? Now equals. Now your area formulas might give you something slightly different because you're estimating. This was an exact answer because it made exactly a rectangle. As you start getting curved shapes, your area estimates might be slightly off from what the calculator gives you. Okay? That is what you're going to type in. Now I'm going to say check, right? I actually typed it in and I got the same answer. Okay. So how do you get this? You press math. I believe it's number 9. F int. And then you have to fill in these parts. That's what you have to fill in. Where do you start? Where do you stop? X. And then right here, that's what you type in, whatever the equation is, the picture. 4 minus absolute value of x. 3. That's what's going into that portion right here. Okay. To do this without me.
Oh, wait.
Four minus x. X. Check, they are the same. Okay, this next one. Okay. So this one is curved. So that's going to be a little trickier. Okay. So 4 minus x squared, so I believe I get these points here at 1, 3, negative 1, 3. Now I do notice it's symmetric, so let's do some area. So 3, and estimate. So I think I'm going to do this as a triangle. That's 1 and 3, so 3. 1/2 base times height. Okay. Triangle. But it looks a little bigger. And doubled, so 10. Plus this little extra, so we'll call it 10.5. Okay, so let's test it. Integral. Negative 2 to 2, 4 minus x squared dx. Okay, math. Number 9. Negative 2 to 2, 4 minus x squared dx. 10.6 repeating. Math frac. So 32 over 3. Right, this is an estimate. That's the actual answer.
I mean, the whole thing is going to be dropping.
Ooh, height. That's just going to be 3 minus 1. Nope. Nope. Okay. Okay, so let's type. Math 9. 0 to 2 root x plus 1.
No, I'm not. The first room wasn't there. Yeah.
2.79.
The legend. Yeah. Legendary asset plan. Yeah, she's got her work on.
Notice the estimate is pretty close. Okay, notice the area is exactly the same as the integral. Okay, so we did 1 square, rectangle, or sorry, triangle, triangle, 1, 2, 3. And let's check it. Math 9, 0 to 2, function, 2.6. So it looks like I must have overestimated somewhere. Oh, I know. It actually adds to 3. Okay, so 2.6 repeating. 8/3. So we overestimated here. The exact answer is 8/3. Okay, so we have one big rectangle and two smaller triangles. So 2 times 1/2. So that gives me 1, okay, for this section right here. Okay, and then we've got 1/2 base times height. So that gives me 1/2. So together, that's 1.5. So now let's test it for real. So -1 to 1. Alright, there we go. Math 9, -1 to 1.
Wait, I think I see that. Yeah. Yeah, no,
Oh, let's try x squared plus 1. So this was an estimate, 1.57. Okay, so 1.57. Last one. Okay, so rectangle, 2 times height, so we get 2. We've got 2 triangles here, so 1/2 base times height, 1, 2, 3. Okay, so we get a rectangle, a triangle. Right, if I plug in these points, 1 squared plus 1 is 2 squared is 4, so I actually get the points 4, okay? So it makes this is actually 3 high. So 1/2 base times height, 3 halves, but I have 2 of them, one on this side, one on this side. So we've got a total, all right? So 1.5 and 1.5 is 3, so we get an area of 5. Let's type it in to check, okay? The integral from -1 to 1. Okay. Math 9, -1 to 1. X squared plus 1. Notice the parentheses here. You've got the original parentheses and you've got the parentheses inside. I get 3.7. Okay. Or 56/15. Now this one seems to be quite an overestimate here, but I guess sometimes that happens.